All right, this video is going to talk about linear programming. Linear programming is a process in which we're going to optimize or maximize or minimize a linear objective function, sort of a goal function, given a set of constraints. So again, we're going to try to maximize or minimize this sort of z equals 3x plus y in this example by only plugging points into that function, into that objective function that would satisfy these inequalities here, or what we call the constraints. Right? They're going to limit what we can plug in. Now, if we take those constraints and we graph them, so notice the middle of the screen here, right, I've got most of this one marked out, what we're going to end up with is what we call the feasible region. If we think x is greater than 0, we're going to be to the right side of the y-axis. Y is greater than 0, we're greater than the x-axis, so we're up in quadrant 1 here. Right? Y is less than or equal to negative 2x plus 12. Well, that means that we're less than this slanted line here, this green line. So now we're down sort of in this triangle, right, in here. And then y is greater than or equal to 2x minus 8. We're greater than the blue line. So notice we're shaded above the blue line. So all in all, taking into account all four constraints, we've basically sort of limited ourselves to be inside of, right, this sort of blue region here, right? We're up in quadrant 1, but we're below the green line. We're above the blue line. Basically inside of this shape here. So what I would want to do then is say, well, there's an infinite number of points there. Why don't we just grab a bunch of points and we'll determine, again, where the best possible point would be. So I'm going to grab points from all of the corners, first of all, right? Because they're my sort of extremes, right? They're the lowest points, the highest points, and same thing left to right. They're the points farthest left, farthest right. I also went ahead and on this table, just this time, grabbed a whole bunch of points from the middle of the region as well. Okay, but you'll notice pretty quickly when we take a look at it, the minimum possible point was definitely at 0, 0. It was one of my corners. And the maximum point down here was 17, right? That was my maximum extreme value. So the answer to my question would have been, what's the largest value of z? Well, z would equal 17. But notice that came from the point 5, 2. That came from, again, another one of the corners of this region, which kind of makes sense. If we're adding x to y, and in fact, we're tripling x before we add it to y, we want the point that's farthest to the right, but yet if we can gain a little bit from the y's, so maybe a little bit upward as well, we want that point because that's going to be our highest possible value. Now, maybe giving up a little bit of x would have gained us a little bit of y, so that's why, again, we want to check the extremes. And the linear programming theorem basically says if you have a feasible region, you should definitely grab the vertices because your minimum or your maximum value will typically come, again, from those vertices, right? Now, mind you, if you get the same value from two different coordinates, maybe every point on that line might give you the same value. So you'd want to check that out. But in the end, what you really only need to check, or the only points I really needed to put on my table, would have been checking that highest point, checking the lowest to the left, again, the farthest to the right and up, and again, farthest to the right and down. So those four corners were really the only ones I needed to really look at. Right? And again, my highest value came in as number 17 here, z equals, right, 17. Now, where could we use linear programming? Well, in business, it's a great idea to use some linear programming. So we've got this snowblower example up top. Basically, and I'm just going to jump to the end of the problem. You can always pause it right now and read through the whole problem if you'd like. But I'm going to jump to the end. It's saying find the number of units of each model of snowblower. So I'm going to call one model X and one model Y. Right? I've got X model that I'm just going to say was my $250 snowblower. Right? And the Y model, right, that I'm going to say was this $400 model that we're looking at. Right? So my objective then, right, function where I'm going to actually get the profit is that when I sell the $250 model, I make $45, right, per model. When I sell the other model, I make $50, right, per model. I'm likely to sell more of the first one, though, even though I make less money on it, because, again, it's a cheaper model, right? I'm going to be able to sell it for less money, and I'm probably going to get a wider range of people being able to afford it. So the question is, what do I want to stock up on? Right? I don't want to overstock any one thing. I want to be able to buy what I need to sell it off and basically hopefully make the most money possible. Well, our constraints are going to be along those lines as well. So we need to write those down. Then we'll get to the graphing portion. Well, the constraints that we have is that, again, we have x plus y, the total number of models that we want to have in stock. Well, we don't want to have more than, according to our problem here, 250 snowblowers. And we also know that, again, in order to even get them in stock, it costs me $250 per X and $400 per Y just to stock them up, right? Just to put them in my store. And again, I can't spend more than my budget just to get my inventory, right? To stock up $70,000 worth. We also know that we can't have less than 0 snowblowers, right? X needs to be greater than or equal, and Y needs to be greater than or equal to 0, which is why we're only going to be in quadrant 1. Now, you can graph these lines in a lot of different ways, right? You can graph them in a lot of different ways. What I'm going to do is go ahead and use some intercepts, because I know very simply this top equation, if X were 0, right, then Y would equal 250, and if Y were 0, right, X would be 250. Just thinking about plugging zeros in for my x's and y's in that top equation, right? If x were 0, it's gone. Y just equals 250. Same thing, plug 0 in for y, leaves you with just x, again, equal to 250. For the bottom equation, you can kind of do the same thing. Again, if I plug 0 in for x, pretty much you would just drop this x term off here. We divide by 400, right? And 70,000 divided by 400 basically is just, let's figure that out. 70,000 divided by 400 is going to be 175, I do believe. 175. But on the other hand, if I plug 0 in for y, right, then I'm going to be taking 250 divided into 70,000, right, and I get 300. So now what we can do is go ahead and plot our points, right? I know that my y values need to go up to at least 250, so maybe count by 50s. We can say 50 is 100, 150 is 200, 250, right? And then we go up to 300 here. And then same idea, really, the other direction should work just fine. 50 is 100, 200, 300 out that direction. So I plot the points at 300 here and 175. Right? I can connect those two dots and make my line. And I know that I'm shaded below there because, again, if I plug 0, 0 into my function, 0 plus 0, right? That would have been this function here, right? I plotted 0, 175 and 300, 0. But at 0, 0, that's still less than 70,000, so I want to shade below that line. The other one, again, I want to do 250 and 250. So let's maybe do that one in purple. 250 and 250. We can plot our line. Right, essentially there. Not the straightest of lines, so I might want to straighten that out a little bit. But again, also, if I plug 0, 0, and 0 is less than 250, so again, I'm going to be shaded below. So essentially, I want to be shaded down here, below the red and below the purple on my graph. So now when I go to make my table, right, the possible feasible points, right, the points from that feasible region that I want to plug in, well, I'm going to say 0, 0. Technically, it touches the shaded region. We also know that at 0, 175, right, that was another possibility. I'm going to plug in 250, 0. Now, notice I don't need to do the 300, 0 because this point over here, right, doesn't touch the shaded region. Only the purple point, right, that closer point, that point at 250 does. So again, I don't need to plug that one into my table. Same thing up on the y-axis. 175 touches the shaded region, but 250 doesn't. That purple line's well above, right, the shaded region at that point. I only want the points from my shaded region, the points that touch the feasible region. But in that case, I also need to know what this coordinate here is. Now you can solve that by just crossing those two slanted lines. You could do that by substitution. You could do that by elimination. But I'll tell you, I did it on my calculator and just went ahead and did it by graphing. Just note that that's going to be 50, 200. Okay. If I had drawn a little bit better line, we might have noticed that it's technically right about here, right? Really. Oh, sorry, 250. Got that backwards there. So again, we're going to plot the point 250. Again, would have been right down there where that blue point was. But that was my 4 corners to my feasible region. Plug those points into 45x plus 50y. You can go ahead and take a minute to do that, or just trust me that if you plug in 0, 0, you'll get back 0. Obviously, if we don't stock any snowblowers, we can't make any money. If you plug 0, 175 in, well, basically 50 times 175, right, is going to be 8750. Again, 250 times 45 plus 0, so all of one, none of the other, will come out to 11,250. And then finally, if you do 200 of the $250 snowblowers and 50 for Y, right, plug in 250. Again, I'm not going to write out the small part there, but realize that you'll get 11,500. So of those 3 actual good options, right, obviously we're not going to want to make 0 money. The highest one is 11,500. And what that tells us is we should stock, right, 200 $250 snowblowers, right, and 50, right, $400 snowblowers. And that will make us the most money. If they actually wanted to know what the profit was, again, that's what this is, right? That's our profit. We would profit about $11,500. I hope that helps you with linear programming. If you want some more examples, I've got another example up on the internet, or you can find some elsewhere. If you have any questions, talk to your teacher. Good luck and have fun.